Welcome, I'm Daniel Pizarro from the University of Alcalá. Today I will be presenting the tutorial on sound source localization as a part of the work we do in the Ruby team in the Erasmus Plus project GEMS. Today I will be guiding you through several examples of how to localize a sound signal from several microphones, and we will do a practical example with the Ruby board. This tutorial is structured as follows. First, we will outline the objectives of this tutorial. Then we will cover the basic concepts related to sound and its propagation. We will explain direction of arrival or DOA detection principles. Following that, we will walk through a DOA estimation example implemented on the Ruby platform. Finally, we will summarize with conclusions and provide references for further study. Let's clarify the objectives of this tutorial. The first objective is to understand the basic concepts of audio propagation. How does sound travel, in fact? The second objective is to estimate the direction of a sound source using a pair of microphones. This is the core DOA technique we'll explore. And finally, we will provide an example code using the Arduino platform, specifically for the ESP32 microcontroller that we have in our Ruby board. It is also important to note what this tutorial is not focused on. We will not cover a general multi-source localization problem, which involves identifying multiple sound sources simultaneously. This is a very difficult and challenging problem. We will also not cover complex acoustic scenarios like closed field conditions or highly reverberant environments. These where sound reflections significantly complicate the analysis. We'll stick to simpler, far-field assumptions. Let's begin with some basic concepts. We start with the definition of sound. Sound is fundamentally a mechanical wave, and it arises from the interaction of particles within a medium like air. Specifically, sound waves are longitudinal waves. This means that the displacement of the particles is parallel to the direction of the wave is traveling. Air molecules are responsible for transmitting these pressure variations by colliding with the neighbors, effectively transferring energy through the medium. The speed of sound depends on the medium properties, its temperature, pressure, and density. As shown in the table, sound travels at different speeds through solids, liquids, and gases. In air, a crucial value that we will use in this tutorial is the speed of sound at room temperature, which is 20 degrees Celsius, and is equal to 343 meters per second. We will use this value in our calculations. Now let's consider our basic setup, a sound source and a pair of microphones. We have a sound source emitting a signal, let's call it S of t, which is a function of time. We have two microphones labeled left and right. dL represents the distance from the source to the left microphone, and dr represents the distance from the source to the right microphone. D is the fixed distance between the two microphones. The signal received by the left microphone is called SL of t, and the signal received by the right microphone is called SR of t. On the diagram, you can see an example of S of t, which is the signal in the source and corresponds to a single frequency. A key assumption in this tutorial is that the signals received at the microphones, SL of t and SR of t, are essentially shifted versions of the original source signal S of t. In this way, SR of t is going to be equal to S of t minus delta R, where delta R is the time shift. In the same way, SL of t equals S of t minus delta L, and delta L is the time shift for the left microphone. These time delays, delta R and delta L, are due to the time it takes for sound to propagate from the source to each microphone. They are calculated as the distance divided by the speed of sound. So delta R equals dr divided by the speed of sound Vs, and delta L equals dl divided by Vs. The plot here illustrates this phenomenon. The red signal represents the propagated signal S of t arriving at a microphone that is 10 meters away from the source, showing a time delay compared to the original blue source signal S of t. Now let's relate the two microphone signals directly. The key idea here is that if SLT and SR of t are shifted versions of the same signal, we can express this left signal in terms of the right signal. The left signal SL of t is equivalent to the right signal shifted in time by the difference in delays. So SL of t equals SR of t plus delta R minus delta L. Delta R minus delta L is called the time difference of arrival between the two microphones. This time difference is directly proportional to the difference between the path lengths from the source to each of the microphones. And this is a crucial formula because you can compute delta R minus delta L as dr minus dl divided by the speed of sound. This relationship is fundamental for estimating the sound source direction, and we will use it next. Let's visualize these properties. Consider the case where the sound source is generally on the left side. In this situation, the distance to the right microphone, dr, is greater than the distance to the left microphone, dl. So dr is greater than dl. This means the sound takes longer to reach the right microphone. Looking at the plot, the red line represents the signal at the left microphone and the green line is the signal at the right microphone. You can see that the red signal arrives earlier in time than the green signal. Let's now consider the case where the source is exactly centered, equidistant from both microphones. Here dr equals dl. The sound takes the same amount of time to reach both microphones, and so the two signals are exactly the same. Finally, let's consider the source being on the right side. Now the distance to the left microphone is greater than the distance to the right microphone. In this case, sound reaches the right microphone first. In the plot, you can see that the green signal arrives earlier than the red signal. So, in conclusion, by observing which signal arrives first and how much, we can infer the general direction of the sound source. And this is basically what we call the direction of arrival angle, and we denote it as theta s. This angle represents the direction of the source relative to the line perpendicular to the microphone array baseline, as is seen in the diagram. Under the assumption that the source is far away compared to the distance between the microphones, this is what we call the far field condition, we can obtain a simple formula to get the angle theta s. The formula is shown in the slide. Theta s equals the arcsine of the time difference of arrival divided by the distance between the two microphones and multiplied by the speed of sound. And remember, this is only valid assuming that the distances dl, dr are much greater than d. So how do we actually measure this time difference of arrival? We will use the cross-correlation function. But what is correlation? Correlation measures the similarity between two signals as a function of the time shift applying to one of them, and it corresponds to the formula that is in the slide. We show next an example of two signals SL and SR and its corresponding correlation function. The correlation has a clear peak at t equals 0. This peak corresponds to the shift between the two signals that make them most similar, and we can use this to find the time difference of arrival. For instance, assume the condition in which dr is bigger than dl. This corresponds to a source which is on the left side of the microphones. If we compute the correlation function between these two signals, and we compute the time at which the correlation has a clear peak, we call it Tmax. This Tmax is directly the time difference of arrival, which is delta r minus delta l. With this, we can compute the direction of arrival next. Now we can summarize a practical algorithm to find the difference of arrival DOA angle theta s. First, we capture the left and right microphone signals, SL and SR. Second, we use the correlation formula to compute the cross-correlation between the two signals. Then we compute the time at which this correlation function becomes maximum. And then we use the formula of the arcsine to compute the DOA angle. Now, let's look at a practical implementation of these principles. We are going to propose a DOA estimation example using the Ruby board. The objective is to capture audio signals from the two microphones connected to the ADC1 at a resolution of 12 bits and a sampling frequency of 30 kHz per channel. We will compute all the steps of our algorithm, the correlation and the maximum of the correlation, the DOA angle, and we will also use the serial port for visualization. As in the other tutorial, we will use the Arduino and ESP32 libraries. Let's break down the Arduino code for this example, starting with the initialization and setup of variables. We set conversions per pin to 1, and the ADC pins correspond to channels 1 and 0, as in the other example. Also, we use n samples equals to 725. Then, lagmax defines the size of the correlation window that we will compute, because we don't need all the samples in the correlation. Then, we set the sampling frequency to 30 kHz. We also set up the speed of sound to 343, which corresponds to room temperature, as we said before. And also, we configure the distance between the microphones in the Ruby board. Also, we initialize the correlation buffer that we will use to store the correlation values, and also the Tmax and zeta s angle variable. Next, the setup function configures the system when the microcontroller starts. We set up the serial communication and the ADC resolution, attenuation, and the pins of the ADC, jointly with the frequency. We also start continuous ADC conversions using the DMA process of the ESP32. Now let's look at the main data processing logic, which corresponds to the loop function. We first check the ICR flag, which checks if the ADC conversion is done. Next, we do the data reading and storage. It reads the results from the ADC buffer, and the raw ADC values are converted to millivolts and potentially centered around 0 by subtracting an offset. This offset corresponds to the DC value of silence levels in the microphones. The center values are stored in the S-left and S-right arrays. A counter N tracks the number of samples that's been collected. Then we compute the cross-correlation. With the function calculate cross-correlation, we find its maximum position to calculate the time delay. We compute with the formula the value for the angle, the DOA angle. Crucially, we have to saturate the values of the argument between 1 and -1 so that they are compatible with the arc cosine. To test this implementation, a simple experiment was conducted. We use a 1 kHz pure tone audio source. We will visualize the values of Tmax and the DOA angle. First, we start with a source position that is on the left of the Ruby board, and we measure a Tmax of around -100 microseconds, which corresponds to an angle of -31 degrees. Then we try another source position that is more equidistant to the two microphones. In this case, we have a smaller Tmax with around 30 microseconds, which corresponds to an angle of approximately 10 degrees. And finally, we test a position which is at 90 degrees and corresponds to a source on the right and a Tmax of 200 microseconds. These results demonstrate that the system can estimate the direction of the sound source based on the measured time delay. So to conclude, we successfully demonstrated how to capture audio signals from two microphones using the ESP32's ADCs in continuous mode, which is efficient for audio processing. We also apply cross-correlation as a method to determine the time delay between the signals arriving at the two microphones. We then calculated DOA angles using the formula we had derived from theory. And we also showed that this can be done in practice using the Ruby board, and this can be applied for various real-world applications, including robotics, robot navigation, and acoustic monitoring systems. For those interested in exploring deeper, here are the references used. Note that reference 2 is a book that can be used to learn more about algorithms for DOA estimation. Thank you for watching. This video was created by the University of Alcalá for the GEMS Erasmus Plus project, which is a collaboration between the University of Ljubljana, University of Alcalá, Teaching Factory Competence Center, and the Delft University of Technology. It is released under a Creative Commons Attribution license. The project is co-funded by the European Union.